I'm Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. AP Physics 1, Unit 1. We're still on free fall, and we're talking about graphing free fall today. I think once you see this, it's going to just click, hopefully, and make sense, and hopefully free fall graphing is much easier for you after this. We hope, right? Okay, so here we go. So we're going to start, instead of spending our time and wasting your time doing a problem that you can already go back in the video and look, we have under free fall problem, it's titled Throwing a Ball Up in the Air. All right, I'm going to go ahead and take that problem, and then we're just going to graph it. I'm just going to do one extra little thing to it. All right, first of all, in that problem, we threw this ball up into the air at 8.5 meters per second. And we found, it asked for what was the time in the air. So if we have this little drawing here, it took off and landed at the ground. It was some device that shot it up straight up in the air. It came straight down. All right, so our initial velocity was 8.5 meters per second. Our acceleration, because this is a free fall, is negative 9.81 meters per second squared. Our initial position was 0 because we were at the ground. And then when it hit the top, it stopped. Because remember, an object that goes up, it's fast, 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 but it slows down, slows down, slows down, stops at the top, and then it comes down and it starts speeding up, speeding up, speeding up as it lands. Okay? And we've mentioned what initial velocity, acceleration, and initial position was. All right, so here we go. We found that the time up was 0.867 seconds in that video, and we found that time down was also 0.867 seconds because time up is going to equal time down as long as they start and end at the same height, and that we're ignoring air resistance. Remember that we are living in this physics bubble, happy bubble, where we are ignoring air, so we can't breathe in this bubble. But anyway, again, welcome to physics. So now we have all of our information. I'm going to do one more thing though. I'm going to want to calculate how far did this thing travel? How high up did it go? In other words, what was its displacement? All right, well, I'm going to use that second you could actually use either. You have the information to use either your second big three, our uniform accelerated motion problem equations, we like to call the big three, the second one or the third one. You could use either, and it doesn't matter which one you use, you get the same answer. But we found, I put in my initial, this is the upside, so we're starting down here with an initial velocity in the y of 8.5. Our final velocity is 0 because it stops at the top to turn around. And then our acceleration is negative 9.81, and we're looking for that delta y. How high did I go? And I get 3.68 meters. Now, if you're looking at this and going, what in the world are all those little subscripts? I mentioned that still in this unit, 2D, which we're going to start posting those videos soon, that I like to use the y subscripts to remind myself that I am traveling vertically, because when we get to 2D, we're going to be doing an x component, a horizontal component, at the same time as a vertical. So I like to keep those separate. If it's too many subscripts for you, that's fine. I do like to tell my students it will help with the confusion in the next section, okay? Anyway, but we have 3.68 meters that we've traveled. Okay, now we're going to graph it. We have our information. We know our initial velocity, our initial displacement, our acceleration. We know our final velocity at the top. When we start at 8.5, we end up at 0. Okay, what does our position look like? Well, we start at 0 right here. Why on our position? Because we're at 0 on our position at 0 meters. We called the ground 0. Now, it's going to look like this. It's going to be a curve because you have acceleration. All right, I'm going to go right to 1 second because on the way up, we just go to 0.867 seconds on the way up. So it's a little bit before 1. Remember, this flat line means that you are at rest. Did we not hit rest when we hit the top? Absolutely, we stopped for just a split second. Now, why does the curve look like this instead of turned the other way? Because as you are going faster, you cover more distance. Right? If you're going 60 miles per hour down the road, you're going to cover a lot more of the road, go down the road farther, than if you're only going 15 meters per second. All right, so we were going faster and then slowed down. We were going 8.5, 7.5, 6.5, all the way up to 0. So we were covering more distance at the first, and that's what this is showing. In this little bitty time here, we covered a lot of distance. All right, but as we get higher, closer to that top, because this is at the top right here at 0.867 seconds, is where we're slowing down and we're not covering as much of the displacement. Okay, perfect. Now let's go to velocity. So now we know what that curve looks like. Let's go to velocity. We start at 8.5. So I am starting up here between 8 and 9 at 8.5. And I am going to 0 meters per second because as I go up, I have to stop to turn around. And I'm slowing down. So look, this is going to be, I'm going to go right before that 1 second at 0.867 because that's when I hit the top. At the top, my time is 0.867 seconds. And again, that's from that problem. You can go back and look at that problem and how to work it. But that is my, now why, so that is my time. And I'm going from 8.5 to 0. This is up. All right, well remember, velocity time, that's change in velocity, rise over run, change in time. That's acceleration. This line is acceleration and it's negative 9.81 meters per second squared because this is a free fall problem. That is our average Earth's gravity. All right, so now look at or acceleration due to gravity, I should say. So now that's a straight diagonal line. Why? Because it's constant acceleration. So then we go down to our acceleration graph and we're like, oh, okay, acceleration is negative 9.81. So I'm going down here and I'm putting in negative 10. And I am at right here at negative 9.81. And I'll just go right to the top. So all this is for the top. Okay, so at 0.867, hopefully that's about where that ended, we have acceleration of negative 9.81. So that is how you graph free fall. Now, to talk about a little bit further, what does my velocity time look like if I'm up and this is the top, right when it hit 0 velocity, we know it's at the top. What did it look like when it came down? Okay, well look, it goes straight down. This, our final velocity, when it's coming down, it starts at 0, but when it's down, it's speeding up. My final velocity is going to be the same speed that I took off as long as I take off and land. It's going to be the same speed, but it's negative because we define down as negative and up as positive. So we have negative velocity now. It starts at 0. It goes negative 1, negative 2, negative 3, whatever, all the way to negative 8.5 meters per second. So we're down here, and this is right before 2. At 1.7 was my total time because it takes 0.867 seconds to come down. So right before 2 at 1.7, this is where I stop, and I am at 8.5. So if this is negative 9 and this is negative 8, I'm right here in the middle at negative 8.5 meters per second. And look, this is one solid constant acceleration, one solid diagonal line because it is constant acceleration, negative 9.81. It doesn't matter if you throw this up, if it stops at it stops just that split second to come back down, or if it's coming down, or you throw it down. It doesn't matter. Your acceleration in a free fall stays here at negative 9.81 meters per second squared unless you're on a different planet or the moon. All right, now here, coming down, it just still remains that straight line to right before 2 seconds at 1.7 because that was the total time in air of negative 9.81. Perfect. Now let's look at one more where we actually, what does it look like if we drop this thing? All right, if we drop this, I forgot my eraser a while ago. If we drop a ball, that means your initial velocity is 0 and it's going down. All right, so we drop a ball, we start at 0. If this is my velocity, so this is velocity time, not position, this is velocity time. I start at 0 and then it falls down and it looks like this. That's what it looks like if you drop a ball. All right, if you throw a ball down, let's say you throw it down with an initial velocity of 2 meters per second. Remember, down is negative, so that's really a negative 2 meters per second. So your velocity time graph would look like this. It's still negative 9.81, the slope of this line. It's going to be the same slope as this line in your velocity time because the slope is acceleration and that's not changing. All right, so if we throw it down though, let's say we start at negative 2 we throw it down, so it starts at -2 and it's the same. It's the same slope because again, acceleration is -9.81 meters per second squared. All right, perfect. That is your how to graph free fall. And hopefully now that you've seen if you throw it up, at the top it's 0. As it's coming down, this is the down part. And then you see one where you drop it and one where you throw it down. Hopefully that's going to really help. And acceleration is going to be the same graph on all of them because it's all -9.81 meters per second squared. Hopefully that helps clear up your free fall graphing. And thank you for watching and happy physicsing.